Let me start recording this one. Yes, so the recording has started. So in the last class, we were discussing about different issues in the dynamic CMOS logic design. So the first one was charge leakage issue. So we have understood because of this subthreshold leakage as well as this reverse bias PN junction, the stored charge which is stored in this capacitor CL, which is basically the input capacitor of the next stage, right? And that charging only happens during the pre-charge. During evolution phase, there is no way that this capacitor will get charged. So we want that the charge which has been acquired during pre-charge phase, that will only conditionally discharge only when this transistor, means only when the pull down network allows it, right? For example, if suppose here the input is 0, then this transistor is off. So then what do you expect? You expect that the charge stored here would be retained, or the voltage will not change here at this output. But because of this leakage issues, we have seen that there is a possibility that this charge will be, there will be an issue of charge leakage, right? And as a result, what will happen to this voltage drop? That voltage drop will fall, right? Okay. Then we have also seen how to stop these issues. So just use this bleeder transistor, right? You can use like this, but this will have some static dissipation issue. So to stop that, you can use like connect this input of this bleeder transistor with an inverter like this. So this inverter is basically a static CMOS inverter. This is the solution. Then we had started our discussion with this charge sharing issue. And what we have seen that you, some of you had some doubt yesterday. So let us start fresh, okay, from here. So charge sharing issue. So this is an dynamic CMOS logic gate, and you know this is an 2-input NAND gate, right? In dynamic CMOS. So here in this circuit you can see there are like 2 inputs, right? Let us say that B input always be at 0. So B is fixed at 0. Say, so this transistor is always off. It does not matter whether this is in pre-charge state or in the evaluation state. However, this transistor makes this input A makes a swing like this. So it swings from 0 to 1. So this transistor after some time it will turn on. Okay. Still, we have not given the input. I am just saying like what we are planning to do. Okay. And this capacitor, right, you can see this is basically the internal node capacitor. So similarly there will be one more capacitor here as well. This is CB, internal node capacitor, right? But we are not considering CB here because we are assuming that this B is 0. So that means this transistor will never turn on. So there will be not an issue of charge sharing between from the CL to the CB. But if this also goes on, then you have to account for both CA and CB. To make our this simple, to make our analysis simple, we are assuming that this B is equal to 0. So that way we are not considering the effect of this CB, right? Okay, and initially we have make sure that the charge stored in the CA and CB are equal to 0. So that way no charge was stored here, right? So but B is kept at 0, and now A has given, A we are planning to give from 0 to 1. Okay, now the first stage is the pre-charge state. So during pre-charge state, what happened? This V out has charged to VDD, right? This C out CL will charge to VDD, and then we have changed the, now we have an evolution state, and during evolution state, say the input combination is like this: A is 1 and B is 0. So when you make A is equal to 1, that means this transistor turns on. So there will be an path, the path which will connect the CL and CA. Now the CL and CA, right, and say like this resistance is pretty small. So that way you can say like there will be no voltage drop, typically no voltage drop between these two terminals. So you can say this and this are short. So if these two are short, then, and if this transistor is fully on, then this potential and this potential has to be the same, right? And the charge that is lost from here, right, that will come, and that will also like means some charge will be lost by this, and that same charge will be collected by this. As a result, the potential means, and this will keep on, the charge will keep on transfer until and unless this two node voltages become equal, right? Provided this transistor is on, right? Okay. Now say we have the CA and CL value that are moderate, okay, and comparable. So if they are comparable and this offered resistance is very low, so that means no voltage drop between these two, right? Then what we can say, so the case 1 would be for moderate case, right? The CL value means this has initially charged to VDD, right? And from this VDD, now it has to discharge because it will share some charge, and that charge will transfer to here, so it will discharge. And say that and say the final voltage after discharging, it has come out to this V out, right? And as you know, this transistor is still on, so these two potential has to be same. So here also, now the potential would be equal to V out, right? Okay, so if you have understood this, then we can apply the charge conservation, because whatever the charge has been lost, that has been initially the how means the amount of charge, and after this distribution the amount of charge is going to be the same, right? So what is the initial charge? It is CL into VDD. So this is the initial case. So initial case, so let us write it by this color, CL into VDD. So that was the initial charge, right? And that charge would be equal to the final charge. So final charge, this voltage is at V out. So it is CL V out plus this also voltage is at V out. So it is CA V out. Right? Okay. So from here we need to find what is V out, the final voltage. So the V out would be equal to how? What it would be CL by CA plus CL into VDD. Right? Then what is the change? Change in output voltage. What is the change in output voltage? So this is basically delta V out. Initially it was at VDD. Right? Now it has changed to V out. Right? So it is basically VDD minus CL by CA plus CL into VDD. Right? So if you calculate it, this CL will cancel from here, right? So you will get CA VDD. Right? So this will be the change in the output voltage, right? When this transistor is still on and this this transistor is still on, right, during the complete scenario of the this charge distribution. Fine. Okay. Now let us come to the other case. Okay, what might be the other scenario? The other scenario might be something like this, that say this CA value is low, right? This CA value is low, so that means whatever the charge is coming, okay, that can make rise this potential quite significantly, rise the potential of this X node X, okay, this node X quite significantly. So as a result, the node X will rise very fast. That will happen, right, if the CA is low. If that happens, then you know this will rise first, and there will be some at some certain point of time, this potential Vx will reach to VDD minus V threshold voltage of this transistor.
Sir, in the first case also, why V out equals to Vx? I mean, previously you told that the charges will be same uh, for both the capacitors, but today I think you were writing that V out equals to Vx. Can you elaborate it?
Today we are writing V out equal to
Vx.
V out equal to V. X.
I mean, after the new
Okay,
charges.
the means the first case.
Yes, yes.
Okay, okay. So think in this way. I think yesterday what happened, I first discussed this one. So maybe that was the reason you have got confused. I have considered the case where this CA is pretty small, and as a result the charge increment, the voltage increase across this CA would be pretty fast. And at certain point this will turn off, the voltage means this transistor will turn off and no further charge transfer is possible. As a result, what will happen, the potential here and the potential here would be different. That is the what I think yesterday, from yesterday's discussion you were referring to. But
Okay,
today,
yeah.
that's what yesterday and after that, I thought then let us not go first to this. Let us first discuss the common scenario and then come to the special case. Okay. Now, you think about it like this. You have two capacitors. You have two capacitors. One is this CL and the other one is CA. So once you close this circuit, right, will the potential here not be same? Shubham?
Yes, sir. Yes, yes.
It will be same, right? Okay. So what is the condition that this potential would be same? The potential would be, the condition is
Which should be
this
true.
this has to be switched on, right? Means this has to
Yes.
be shorted, right? Then only the potential here and potential here would be same, right? But suppose in some, if this switch is such that it was turned on initially, okay, so that this voltage was rising, and then what happened, it has turned off again, then what will happen, then there might be possibility that this voltage and this voltage are not equal.
Yes, sir. Understood.
Okay, so then this is the general case which we have discussed, this case 1, right? Now if you consider the other case, right, where, right, we are considering that the CA is small. So if the CA is small, then due to this charge transfer, the rise of this Vx would be much faster, right? And certain point of time, this Vx might reach close to this VDD minus VTH. So this is on, so this is VDD minus VTH. So that means as soon as this Vx reaches this point, this transistor would turn off, right? So once this transistor turn off, then no further charge transfer can occur, right? So in that case, what can we write? Again, we can write, okay, so in that case, we have understood at least this part, right? Here, this Vx would be equal to VDD minus VTH, right? And here, the final value, say again, it is somewhat like V out, right? Then whatever we have written yesterday, that still holds, that this initial charge was CL into VDD, that would be equal to the final charge. So final charge is the charge again stored in this CL, which is CL into V out, plus the charge which is in this CA node capacitor, which is CA into VDD minus VTH. Okay, maybe I will write it here. So in this case, so it will be CL VDD. This would be equal to CL into V out plus CA into VDD minus VTH. Right. So from here you can find what is V out. So after that you can also find delta V out. Delta V out would be equal to VDD minus V out. Fine. Okay. So then how we will understand that which of these two scenario means which case is going to occur, like this, whether it is case 1 or case 2, right? So obviously we have understood here one thing, that is that this delta V out would be equal, this delta V out is the this general most, like is that this is the most general case. Okay. Now, tell me one thing. Okay, let me write it. Okay, I think yesterday I have written it here. So let me see this, or if I can copy this one. 1 minute. Right, so I will keep it like this. Okay, so this is the same thing that we have done yesterday. So you can just check it out, right? Then finally, if you find delta V out will comes out to be like this, right? Now the situation. Okay, before we say like which condition is going to dominate in what case, let me ask you one thing. Here, can you comment for case 2? What would be okay, not I don't have to write all these things. I can just simply write. Can you comment on this change in the value of change in delta V out with respect to this threshold voltage? Means how is it related? Is it greater than delta V out is equal to VTH, or delta V out is less than VTH for case 1? Can you just think for a minute and then reply and then answer this question? So for case 2, when this voltage is rising to VDD minus VTH, right, and this transistor turns off, no further charge can transfer, then what do you think would be the change in output voltage here?
The delta V out is less than VTH.
Delta, very good. Delta V out is less than VTH because see, if this transistor has not turned off, then further charge transfer would have occurred, right? So that means this potential has to be higher than this. So this potential is already VDD minus VTH, right? So delta V out, so the change in here means this potential has to be higher than VDD minus VTH, right? So that way you can say, right, for this case, the case 2, delta V out is less than VTH. Very good. Then similarly, can you comment here delta, what will be the relation between delta V out and VTH? Anyone?
Delta V out is greater than VTH.
Delta V out is greater than VTH. Yes, obvious, right? Delta V out is greater than VTH. Okay. Then, but this is the most general case, right? This is the general expression, right? Delta V out equal to this. But if I ask
Sir,
then, huh?
sir,
Hmm.
so this delta V out is for the CA or CL?
Delta V out is the change change in output voltage, change in the output voltage node. So it is basically this change in V out here, not this one. See, that's what we are doing, na? Delta V out equal to VDD minus V out. So VDD was initial, V out is final, right? Okay. So what I am trying to say, see, for case 1, this is the criteria, delta V out has to be greater than VTH. For case 2, the criteria is delta V out has to be less than VTH, right? So if we say like there will be some situation where this delta V out would be equal to VTH, right? Then that would give us the boundary condition, right? Whether this case 1 is going to happen or case 2 going to happen, right? So the how do you find the boundary condition? You can find the boundary condition by making equal to this, making delta V out equal to VTH. So boundary condition is make delta V out equal to VTH. Delta V out from case 1, because that is the general most general case, right? This is like we have fixed here to this, so this is not the general this is not the general case, right? So case 1 is the general case. So make delta V out equal to VTH. So what is delta V out? CA by CA plus CL into VDD. CA by CA plus CL into VDD, that is equal to this VTH. So from here you will find the ratio of CA and CL. So that comes out to be VTH by VDD minus VTH. Right. So let us just take some example. Let us say this VDD for some case equal to 2.5 volt, VTH equal to 0.5 volt. Right. So that way CA by CL comes out to be, this is 0.5 and this is like 2.5 minus 2, this is 4, right? So this is 1 by 4, right? So this is 0.25, right? So if this CA by CL ratio, so if this CA by CL ratio, this is smaller than this 0.25, okay, then delta V out would be equal to CA by CL into VDD minus VTH. Then this condition will happen, right? Otherwise, the case 1. So means this is basically the case 2. Otherwise, the case 1 will happen. Yeah, folks, is this part clear to you now? Yeah, who can tell me? Okay, let me ask the other means the question in other way. Who have not understood this part? Please raise your hand. So no one is raising his or her hand. So I will assume that this part is then clear. Okay. So then let us move to the next section. Okay. So here on also, right, you can okay, where is that thing went? Yeah, 1 minute. Yeah, so you can see this, right? When the CA by CL is much less than 0.25, that means, you know, when this CA is actually quite small. So this number itself is quite small, right? So that means CA is, no, see the ratio. Ratio is 1 by 4. So when this CA by CL ratio is even smaller than this, that means CA is much smaller than this CA, then you know the condition 2 or the case 2 is going to happen, where the voltage rise here may be so high that this will reach to VDD minus VTH, and which will turn off this transistor, right? Otherwise, if this ratio is higher, CA by CL ratio is higher, then there will be a distribution. This transistor will not be turned off, and the final voltage across this and the final voltage across this Vx would be the same. Right. Okay. Then solution of this charge sharing issue. So we have already discussed yesterday's class. The take and identify the critical node, just pre-charge it. Now, another important thing that we have discussed, but I just want to briefly go through it once again, so that it would be easier for us to continue with the next section, because that is how we can introduce why domino logic is required. Okay.
Sir, can you go upper page?
Up
Upper
again
page.
here.
Yeah. Yes, sir. Okay. Okay.
Okay. So what is the the question is now, this is the stage 1, right? This is the stage 1 of like dynamic logic. This is basically an inverter, right? This is another stage, this is stage 2, right? So stage 1 is driving stage 2, right? And both are dynamic means dynamic CMOS inverter only, right? So here we can clearly see, if the situation, like if the condition is like this, and the clock is like this, V in is like this. So this is basically the pre-charge state. This is the evaluation state. This is the next cycle. Okay, right. And during this pre-charge, we know, so okay, let me put it in this way. So here we have two outputs, output 1, we have identified it output 1, output 2, this is output 1, this is output 2, right? So during pre-charge, what will happen? During pre-charge, this PMOS will turn on for both, right? And it will charge the output capacitor here and the output capacitor this one to VDD, right? So that means during pre-charge state, both output 1 and output 2 will become close equal to this VDD, right? Okay. Now, see what is happening during evolution phase. That means evolution phase entered here. So when the evolution phase is entered, so you can see here this V in is already in means one state, right? So that means V in is equal to VDD. So that means this transistor is on. Now we are evolution state. Clock is also on. So this transistor is on. This transistor is on. So the capacitor, which is this capacitor will discharge, right? So this capacitor will discharge, but this it will take some time, right? So it will gradually discharge, right? Now that up to what point it can discharge? So that we have already discussed. For dynamic logic, it can discharge up to the switching threshold. Switching threshold is basically the threshold voltage of the transistor. So it can discharge up to this part, right? Now see what is happening for the next stage 2. So for stage 2, when it has entered into the evolution state, what it is seeing? It is seeing that this output is still 1, right? See here, output is still 1. So output is still 1, that means this is on, right? Now we have entered into the evolution phase. Evolution phase, this transistor is also on, clock is equal to 1, this transistor is on. So this is on, this is on. So that means this capacitor will also start discharging. This capacitor will also start discharging. So you can see this output 2 will also start falling, right? Output 2 will keep on falling until and unless the voltage here or this output 2, until and unless this output 2 is not reaching the value of threshold voltage. So until and unless it is reaching the threshold voltage, this output node will keep on discharging. This output node will keep on discharging, right? So that's what I have shown here. The output node will keep on discharge like this, right? Okay. Now see the what will happen, what will be the scenario during the static means during the steady state condition. So during the steady state condition, this is say we have reached the steady state for in this time. Okay, so here we are still in the evolution phase. V in is 1, right? VDD is this value, VDD is this value, which is quite close to equal to 0, right? And what is happening to this VDD, Vout2? Vout2 is also pretty low compared to this VDD. Right now, see what is our expectation? We have applied here 1, so output is expected to be 0. So this 0 is been fed here. So here the output expected to be equal to 1. So 1 means equal to VDD. But see what is happening here in during steady state, the voltage that we are getting is much lower than that of VDD. And this lower voltage, once it has discharged, means once this output node has discharged, right? This is the dynamic logic, right? So there is no connection between VDD and CL during this evolution phase. Next connection is going to happen during pre-charge, but during evolution phase, this has already been discharged. So there is no other way that you can charge it again. So that means you have a much lower voltage, to drive at this output, okay, which has been considered as 1, but if it falls too far, maybe for the next stage it is not even considered as threshold logic 1, it may be considered as logic 0, right? So those issues will come if we use this dynamic logic, simply like if you cascade this dynamic logic like this, right? So
Sir,
then
if you
what?
arbitrarily increase the value of CL, then the discharging time increases. Then can that issue be solved?
Yeah, but yeah, if you are saying you are saying that we can increase the value of CL. Okay.
Yes.
So increasing CL means it's basically the next stage, right? So next stage you are increasing this transistor width, right? So that means that
Yes.
will it not affect the delay and all this stuff,
Okay. Yeah. Yes.
right? Okay, right. right? And even if you suppose increase it, but still it will discharge. Maybe it will discharge slowly, but it will again discharge, right? Maybe not this part, maybe like this, then, isn't it, Shubhayan?
Uh, yeah, sir, I was basically, yeah, sir, but basically going to that lower value, before that, the V out one will go to VDD, I mean, V out one will go to VTH.
V
So,
out one will go to VTH, okay.
yes, so then already the transistor will be cut off. So there is no point of discharging after certain time. So,
Right, but how are we making sure that this will be the first stage? Maybe this stage is been driven by like another block which is before that, which is
oh,
also dynamic in nature,
yes, yes, yes,
right?
yes.
Right. Right. So have you identified the one thing, like what is the problem? The problem being here is like for dynamic logic is that during pre-charge, we are making all the output equal to, or we are making all the output equal to 1, right? So we are making all the output to be 1 during pre-charge. Then what will happen? During evolution phase, this 1 will not go to 0 immediately, right? So this will cause and discharge, when cause and discharge means undesired discharge of this from the second transistor, right? Now this might cause for the next stage, like that, right? So the primary issue that is here for the dynamic logic is that during, means I'm saying in terms of cascading, is that we are using pre-charge, and during pre-charge we are making intentionally making this output to be equal to 1, right? And these are n type transistor, right? So if we are making one, that means VDD, so that obviously that makes the next transistor turn on, right? Next transistor so immediately, once you are in the evolution phase, immediately this is on, this is also on, so the next stage will start discharging. So to solve that, one new type of logic has been proposed, which is called the domino logic. Okay, so this domino logic is not very difficult. What it says is something like this: that you have this network, like similar. If you consider just remove these inverters, right? Then basically this is similar to what we have discussed here. Exactly similar, right? But domino logic says that don't connect it like this, but just use an inverter in between. Inverter means this is a static CMOS inverter. Okay, this is not a dynamic inverter. So use an inverter here. So what will happen? So during pre-charge, this will become, so pre-charge. So during pre-charge, during pre-charge, this output, this node will become 1. Now this we have an inverter, so this will become 0, right? So this is 0, right? This is the pull down network. So 0 means 0 voltage has been applied, and pull down network is made up with an NMOS. 0 cannot turn on this NMOS. So the question of the further leakage, that is not there, right? So then by simply introducing an inverter between, means static CMOS inverter. So these are again static CMOS inverter. You can simply actually remove that issue. Okay. Now, yeah, there are few things like, then why it is called actually this domino logic. Okay, let us also try to understand that. So, okay. So, do you know what do you mean by domino? Anyone like falling dominoes? No. So it's basically, suppose you consider like childhood, you have definitely have played. Suppose you have this type of bricks, na. So if you place the bricks like this, place the bricks like this, then you give a push here, like this brick will touch this. Okay, this brick falls, this touches this. Now this will fall on top of this, right? So one after another, right? It will keep on, like this will fall on this, now this will fall on this, now this will fall on this, right? So that means you give a push here, this gives push here, so this will transfer to here, this will transfer to here, this will transfer to here, this will transfer to here. So because we'll get some similarity here, as we will discuss, we'll see. Okay, here, because once you do a change, that change will propagate one after another. So that is why this logic is called this domino logic. So let us see that how this is happening. Okay. So during pre-charge, so we have seen that here it is 1, here it is 0, 1, 0. So let me write it here as well. So this is 1, this is 0. Okay. And then we have gone to the evaluation phase. Okay. So during evaluation phase, this transistor is off, this transistor is on, and say the input combinations are like that, the whole input combination is also 1. Means this complete pull down network is 1. That means this capacitor now can discharge. So this capacitor means here the capacitor of this input inverters. Okay, this can discharge. So here when it will discharge, then what will happen? This 1 becomes 0, right? This 1 now fall to 0. That makes this 0 to 1, like this makes this 0 to 1. And say this 1 can make this pull down network. The other inputs are such that only it was waiting for this input, and once this input become 1, this pull down network is also on. So we are in the evaluation phase. This is already on, this is already 1, 1, 1, right? Then what will happen? When as soon as this become 1, this will also start discharging, right? That means this 1 will fall to 0, and this 0 will become, because of this inverter, become 1, right? So you can see this. If you consider the next stage, that will also, like, you can explain it in a similar ways. So you can see here. So first you give some input, that change is happening here, right, in the first stage. Based on that change, the next change is happening one after another, right? So with similar to that, this falling domino, then this type of logic is called this domino logic. Okay, so here let me ask you one question. Can you comment on what would be the TPHL for this domino logic? I hope you recall, like, what is TPHL? It is the propagation delay for high to low. So what is the propagation delay high to low, or what do you expect at least? What do you expect for the propagation delay high to low for this type of domino logic? No answer? Yes. Arsh, can you hear me?
Yes, sir.
Yes, please comment on this.
Sir, I'm thinking.
Okay. Shubhadeep? Shubhadeep?
Yes, sir.
Yes. So, what is your view?
So the
Okay.
propagation,
How do you calculate delay with respect to what? Shubhadeep? With respect to what you calculate delay?
intrinsic delay,
Huh? Sorry?
intrinsic delay TP naught.
Yeah, that is fine. But with delay means with respect to input, na?
Yeah,
You remember between the 50% change of this input and output, na?
yeah, yeah.
Right. So inputs are here, right? So input is here. Okay. And output is which one output here? This one or this one? So this is the output, right? So this is the output. So when this input is rising, this output falls. Okay. So can you give me some example during evaluation phase when this input is becoming 0 and output is changing like this? 0 to 1. No, yes, yes, no, what?
So can you repeat the question once more?
Yes. So can you comment what would be this TPHL? TPHL for this type of domino logic, or what do you at least expect the value of TPHL?
It
Okay, what do
increases
you mean by TPHL? When the output is changing from, please say it with me, when the output is changing from
1 to 0.
high to low, when the output is changing from high to low. Okay. Now, for here, output has to change from high to low, right? And so that means it has to change from 1 to, it has to fall to 0. Now tell me, is it possible for any input combination during evaluation phase that this input become like 1 to, this will change from 1 to 0? Okay, for it to happen 1 to 0, you are not getting this point. Just for like 1 to 0. If it has to fall 1 to 0, this output has to go from 0 to 1. Okay. When this output here, this output goes from 0 to 1 during precharge. Isn't it,
Yes,
Shubhayan?
yes,
Right?
yes.
During precharge only, this output goes from 0 to 1. Right? So that delay is associated with during in the precharge phase. Right? You think about it during evaluation phase, can you make this here, can you make this node voltage change from 0 to 1? No, right? That is the whole funda of this dynamic logic, na?
Yes, yes,
That dynamic logic in the evaluation phase, it can only discharge, right? It cannot charge,
yes, sir.
right? So if you consider then this output can only fall with respect to this input, right? So you have this TP, um, you have all, means it can only rise this output here. This output can only rise, right? So basically it has TP low to high, right? Is TPHL is equal to 0, right? As per the delay definition.
Yes, sir. Understood.
Right. Okay. If you have understood this, very good. Then let me ask the next question. The next question is, here we have a clock, right? Means we have a clock and we have given this clock to an NMOS. Now just think about it. Is this NMOS really required if you are using a domino logic? What was the function of this NMOS? What was the function of this NMOS in dynamic logic? It seems you are forgetting many things. What is the function of this NMOS in dynamic logic? Function of NMOS in, yeah, that bottom NMOS. Huh? Let us write it here.
In pre-charge, in such that in pre-charge state, it should not, I mean, uh,
Right, right, right. So what is the
Capacitor should have
function of bottom NMOS in dynamic? Right, you are right. This logic. Say, let us consider a simple dynamic logic which is an inverter. Okay. So let's see this case. This is a PMOS. So this is clock. This is clock. This is output. This is input. This is VDD. Right? Okay. So this is the question. What is the function of this bottom NMOS? That is this one. This bottom NMOS in the dynamic logic. Right? Okay. Now say this transistor. Okay. Or this Vin. This Vin is from the beginning itself is 1. Always 1. Right? Now what will happen during pre-charge? During pre-charge, clock is 0, clock is 0. Pre-charge, clock is 0, clock is 0. This transistor is off, but this transistor is on because it is always on, right? And we have a path from here which can charge this capacitor, right? We do not, as this transistor is off, so there is no path from VDD to 0, right? Now you think about it. If you have removed this, what will happen? This is V in, this is VDD, this is clock, right? And you have this capacitor, right? Now here, this can do a charge, but as this is always 1, always say 1, okay? So you have a, this transistor is also 1, right? So you have a direct path from here to here. So you have static power dissipation issue as well, right? So, and this is on, and depending on what is the size of this, it might happen that this is not at all actually charging. The complete thing is been passed to here, right? So that is the utility of this bottom NMOS for dynamic CMOS logic. Now the question is this NMOS redundant for domino logic? Is this NMOS is necessary? So is this NMOS necessary in domino logic? Okay, so please think it over. Like, what is the function this NMOS is our NMOS is performing? Based on that, try to answer this question. Is this NMOS really required in this domino logic? If yes, why? If no, then also why? Okay. So that issue, that cascading different dynamic logic, that issue can be solved using a domino logic, right? Similarly, another logic has been proposed, which is called the NP CMOS logic, right? So it also performs solve the same thing, the cascading issue, but it do it in a different way. For example, and it is also pretty pretty easy to understand why this is working. See here, this is the as usual. This part is as usual, right? We have noticed this part, but if you notice the second one, we have used here this pull-up network. Please check it out. We have used here pull-up network. Pull-up network means basically it is the PMOS network. You remember this for any static CMOS design, we have designed it like this, na? VDD. So we have here V in, we have here V out, right? So this is that pull-up network, right, which is made up of this PMOS. So that part has been incorporated here. And the other one, which is this pull-down network, which is constituted by this NMOS, that is been taken, considered here, pull-down network, right? So basically what is happening, you see here, during pre-charge, so during pre-charge, this clock you have given 0, you have given here 0, right? So during pre-charge clock is 0 0, right? So when you have given 0, then see what is happening. This capacitor, like the capacitor associated, which is connected to the next gate, that will charge. So this become 1, right? So the capacitor becomes 1. But here we have used the pull-up network. Pull-up network consists of PMOS. So this is a PMOS where you have connected 1, right? So if you have connected 1 in PMOS, that makes this transistor off. So that discharging issue of this output, that is not going to happen here, right? Okay. Discharging or charging, yeah. Discharging or charging issue not going to happen here, right? That you have understood. Okay. Next, see what is the next change that we have done. We have also altered the clock. Alter the clock means if you are applying here clock, next stage we are applying the clock bar. So during pre-charge, you have given here 0. So basically during pre-charge, you have this clock bar. So clock bar is basically equal to here, then 1. This is also equal to 1. So you have given here 1. So that means this transistor is off. But you have given here 1. That means this transistor is on. So that means if something is there in this node, that will discharge. Right? So basically you are charging this node, you are discharging the next node. Okay? Okay. Now, in evaluation phase, what will happen? In evaluation phase, you have applied here 1, you have applied here 1. That makes this transistor off, this transistor on. Now here, in evaluation phase, this clock would become 0, this clock bar become 0, right? That makes in evaluation phase this transistor on, this transistor off, right? Here this is off, this is on. Now depending on the inputs, here which was earlier 1, that can discharge, depending on this input values, right? Okay, but see what is happening here. Here depending on these values in the evaluation phase, this is already off, right? So there is no question of further discharge, right? But this transistor is on. So depending on whether this pull-up network is passing, means is allowing this current to flow through this or not, depending on that, this capacitor will charge, right? So basically the issue, I think you are able to understand, right? That basically the issue was happening there because all the MOSFETs in domino logic were not domino logic, in normal dynamic logic gates were this NMOS. So if you are during pre-charge, the next stage, that pre-charge will also turn on the next transistor. So obviously if it is not an NMOS, if it has a PMOS, right, obviously that could have solved. Like you can guess that thing from here. So this is that NMOS, this NPMOS logic, right? And here, please make sure one thing, that for the pull down, means for the first case, when you are using the pull down network, the output has been taken from here. When you are using the pull up network, output is taken from here. Okay. Now the next important thing comes here is, suppose from this node you want to drive other n blocks. Okay, you want to drive other n blocks. Then you have to use again an inverter, other NMOS block, similar to that domino, right? Are you getting my point? So after this, suppose if you want to drive another NMOS block, means pull down network, then you know what is the solution. Use an inverter between them, like domino, right? So like domino, you can use this other NMOS block. So similarly here, if you want to drive from here other PMOS block, then use an inverter here, like domino. Okay. So here, one thing I would like to say, this we are doing this domino dynamic logic by using this pull-up network only, pull-down network only. But please think about it. Can we also do, or can we also use pull-down network and make this type of domino logic? Or can we use only the pull down network and make this dynamic logic gate? Then what would be the connection? Where from we will take the connections? Is it from here? Okay, like for inverter, or will it from here? So that with this, I would like to end this part, this dynamic logic part. Okay, and I will also encourage you to please read it from the book. Okay, so that if you have some doubt, means if some doubt arises later stages, you can always ask it. Yeah. So any question that is coming right now in your mind? Otherwise, we will move to the next section, which is a pass transistor logic. No. Okay. Good. Then let us start with this pass transistor logic. But yeah, pass transistor logic. But it's already 11, so maybe we can take a 1 minute break, right? And we'll come back in 1 minute. Right. Okay, so I think we can start, right? So what is this pass transistor logic? Okay, before introducing this pass transistor logic, let us just uh, review, very small, quite a small thing. See, so far we have discussed static CMOS logic, dynamic CMOS logic, right? In either case, the inputs, if I am writing inputs, then why I am writing this, right? Inputs. All right. Okay. Again, only there is only one input, so it should be input only. Yeah. So say this input, okay, for this case, or inputs where you have multiple like transistors, those inputs we have always given to the gate terminal of the transistor, right? So let us say like put inputs applied to gate terminal, isn't it? We have always applied it on the gate terminal only. Gate terminal, right? Either it is PMOS or NMOS, always applied to the gate terminal only, right? So far, right? But in pass transistor logic, we are not going to obey that rule or follow that rule, right? We obviously will apply the inputs to the gate, but at the same time, if possible, we will also use the inputs or outputs. We will take it from the source and drain terminals. Okay, so let us see one example. Okay, then this thing would be clear to you. Say, if we consider a circuit which is like this, both are NMOS only. and here say we have given A, here say we have given 0, here we have given B, here we have applied B bar. Okay, now let's see what this circuit is doing. Okay, right. So now let us say this A, B, and this is F, this A, B, and this is F. Okay, so for this, let us say this A is 0, B 0. Okay, so when this A is equal to 0, when this A is equal to 0, B equal to 0, so you give, okay, let us see first B equal to 0, because B is been applied to the gate, right? So B equal to 0, so definitely this transistor is off. B is equal to 0, B is equal to 0 means this transistor is on. So this transistor is on, and here 0 has been connected, so this transistor is off. So this is a high impedance, right? Means this is off, so quite a like resistance is quite high. But here this is on, so and here you have applied 0. That means 0 has been now connected with this F, right? Now let us say 0, 1. So here this you have applied this 1, okay, to this B. That makes definitely this one to be like off. This is B bar, right? And that makes this is on, right? So when this is on, right, this transistor is on, so it has been now been shorted with A. But what is the value of A? A is equal to 0, so that makes this is, it would be 0. Now let's say 1, 0. Again B0 means only this transistor is on, right? So this transistor is on, this transistor is off, so it does not matter what is the value of A, right? So here B is equal to 0, this transistor is on, so that makes this output is equal to 0. Now we apply 1, 1. Okay, we apply here 1, we apply 1, that makes this transistor on, this transistor off, right? Now this is connected with A, and this is connected with A, and A value is A is at it's 1, like A value is 1 now here, right? That makes this is 1, right? So obviously you can see basically from this truth table, so we are getting an AND operation between this, right? So you think of implementing a AND gate in static CMOS logic, right? So first make NAND and then invert it. So to make 2-input NAND, how many gates are required? 2-input NAND, how many gates?
4.
4 plus 1 inverter. So 4 plus 2, 6. See here we have used 2 transistors. Okay, and though you can comment a lot, we have used B bar, so let us say one more inverter, say that is static inverter only. Okay, so 2 transistors, so total 4 transistors. So definitely you can see by using this pass transistor logic, there is a possibility that we can reduce the number of transistors which is required. Less number of transistor means less capacitance, faster might be the speed.
So here, how is it for?
Sorry.
Here we are requiring 2 transistors, right?
Here we are
Requiring 2 transistors.
2 transistor, but suppose if you are considering B bar, then
Okay,
from
yeah.
B, if you have to make B bar, so 2 more transistor for inverter.
Yes.
Right. So that is how you can like, I mean, basically you are getting it like this. Okay. Now, if I ask you, okay, like this. Okay, I have shown you this one, so now this would be very easy to you. But if I have shown you this one earlier, then it might be for not that way easy for you. Okay, suppose if we have implemented only this part. Okay, so when B is equal to 0, okay, or say when this B is equal to 1, okay, when this B is equal to 1, then F would be equal to the value of A, right? So that means when this B is equal to 1, so when this B is equal to 1, this value depend on this value of A, right? Basically what I am trying to say, I think that question is no longer relevant here, because I should have then first told you this and then would have asked. My question was like, is this part, the next part is really required? is this part really required to implement and get. So in many cases you will see that. So if you are implementing some gate, you have to make sure that you are getting all the combination for the truth table, right? Otherwise, some cases you might happen that you are checking like some of them and only using one or two transistor you are getting like all the combinations are coming correct. So you are thinking that okay, my this design using pass transistor logic is done. But that is actually not a correct way to do that. If you want to do this, so you have to check for all combinations of A and B and see that you are getting all the required outputs for all different combinations of A and B or not. Okay, this is just for cross checking. Okay, so anyway, this question is no longer valid because I have already drawn this circuit. Right. But
So
here
basically,
is,
if we have some don't care conditions, then we can use the something like the second one, right?
if we have some don't care combination, yes, but you have to make sure that don't care combination does not yeah, you have to then like for example, only with this, okay, only with this, what are the combinations you are getting here?
0 uh, 0 1 0 1 0 1
So you are
0
getting
0
this,
1 1.
okay, let's see that here. You are considering here 0, okay, B putting 0, then what is the value of F?
It should be cross. It is floating.
It is floating, so it is cross. So that way you are not getting this one, right? Okay. What about the next one? Yes, you are
0
getting it. You are getting this, na? Okay. What about this one? This is
cross.
also you are getting, but you are getting this. So you are getting 2 out of this 4. Right. And if it happens that the don't care combination falls here and here, then why can't you? You can.
Okay.
Right, okay, but here is like, so it looks pretty easy, right? We can design even the logic level like this, right? But the issue is this. Say this is okay, this is B, this is A, this is F, and with this F you have a capacitor connected, okay, and this is V out. Right. Say B is equal to 1. B1 means VDD.
Sir,
Say,
also one more question. Aren't we neglecting VTH here?
are we not neglecting VTH, threshold voltage?
Yes, sir.
What do you mean by neglecting? Like
Like,
I am saying logic 0. So this logic 0 means it is very close to 0. Logic 1 means very close to 1. I am not saying 1 is equal to VDD. Okay, so
okay.
yeah, I understand what you are trying to point out. Yeah, I am actually discussing this thing right now. Okay, that very good. So here, see, I have applied here VDD and I have applied here VDD because we are saying like both A and B are at this logic 1. So this is gate, right? This is gate, this is drain, this is source, right? So you know that now this and say this initially this capacitor was discharged initially. Discharge initially, okay. Then what will happen? This capacitor will start charging, and you know that there has to be one threshold voltage difference between gate to source, right? So that way the maximum voltage that you can reach here is what? That is VDD minus VTH. Yes, I think Shubhayan, I think you were trying to like point
Yes,
out
yes,
this one, right? Right.
yes.
So there will be one threshold voltage drop, but still this is very close to logic 1, because if we just think from the static CMOS perspective, right? If it is VDD, then the logic threshold is around VDD by 2 from static CMOS point of view, na? Right.
Yes.
So we are basically operating somewhere in either here or here, right? Basically here we are on threshold voltage below VDD. So it is still like can be considered as logic 1. right? So this issue is here, right? Okay. Now suppose you want to drive. This is A, this is B, this is F. Okay. So you want to drive with this F another NMOS, and say this is say D. Okay. And then so maybe then I will put it C. Okay. This is C, D, and this is now F. Right. So if you connect it now like this, say the situation would become even worse, because here there will be, and say that all are equal to 1. Okay, these are equal to, all are equal to 1. Then there will be one threshold voltage drop. So that means it is VDD minus VTH. And again here there will be one threshold voltage drop. So the overall would be VDD minus 2 VTH if the threshold voltage are same. Right. So if you are making the pass transistor logic, you have to be careful that you are never going to connect a pass transistor, means a output of a pass transistor logic should not drive the gate of another pass transistor logic, right? So if I want to write it here, then maybe I will write it like this. Pass transistor gates cannot be cascaded by connecting the output of a pass gate, means pass transistor gate, to the gate terminal of another pass transistor, right? But however, this issue is not going to be a prominent one if you are trying to cascade this logic like this. Say if you have A here, if you have B here, then if you have C here, then if this is 1, this is 1, say all of them are 1, then here the voltage that you will be getting, that is only one threshold voltage below. So if you want to cascade, so cascade like this in series, not in this fashion. So this is not allowed for cascading. This is you can do, right? And after that, it will be good to use an inverter or two inverters if you want the same thing, means the same polarity, right? To go back, means to restore this VTH voltage, like to restore this drop in VTH, right? You know that, right? How an static CMOS can do that, right? So I hope this way it is not, this is clear to you that why this is not a visible way to connect it, but this looks like more or less is possible, right? We can do it like this, right? So for almost all the transistor, means for almost all the logic gates, we have discussed the VTC, which is the voltage transfer characteristics, and it is also important, right, from understanding point of view. So here this is the same thing. If you notice it carefully, this if you this one and this one are actually same. See this one, right? What I have done extra, just I have added one inverter to show that it is coming through an inverter, right? This is basically, otherwise it is the same thing, right? So this is also pass transistor logic gate, and this is an AND gate, right? And say here the all VDD means 2.5 volt, threshold voltage means 0.5 volt, okay? And now we have to draw the so, and you have to draw the V out versus V in, okay? So again, like we have, you recall, right? We have done for static CMOS, for NAND gate, what would be the VTC? There we have seen the VTC would be dependent on the input combinations, means whether the input are, suppose A and B are changing simultaneously from 0 to VDD, or the input A is fixed at VDD, only B is changing from 0 to VDD, or B is fixed to VDD and only A is changing from 0 to VDD. So depending on these combinations, the VTC will change. Right. So for example, let us say for the first case that we will assume B is equal to VDD and A is changing from 0 to VDD. This is case 1. Okay. So case 1 is B is fixed to VDD and A is changing from 0 to VDD. Right. Okay. Now for this we have said A, this is equal to VDD, so that means this is 1, right? And A is changing from 0 to VDD. Okay, so this is on, this is on, this means this transistor is on. Okay, now this is 1, this is 0, right? And this has been connected with here, so that means this transistor is off. Case 1. Okay, so if this transistor on, then we can say like this will behave simply like a resistor, and then A is somewhat been shorted with F. Shorted means have some resistance, but whatever means how A will change, F will follow that, right? So from that point of view, can we not say that this F means the output, right? This is basically the output, right? This output will follow. Okay, let me use the red one only. Okay, the output will follow the input, right? The output will follow input. Now again, here is some constraint. This output, this is 2.5, right? This one means 2.5 volt, right? So, but we know there has to be one threshold voltage drop. So that way this voltage can reach maximum up to 2 volt. So that's what we have stopped it at 2 volt. So at 2 volt of this input, output reaches to 2 volt, and here it stops. Now if we further increase it from 2 to 2.5 volt, then the output is not going to change. Right? I hope this case 1 is clear to you. Okay. Now then let us say case 2. Now in case 2, let us say assume that this A is being fixed to VDD. I am using V capital DD. V capital DD, and B is changing from 0 to VDD. Okay. So A is fixed at VDD. So means A is basically equal to 1. A is equal to 1 and B is changing from 0 to VDD. Very good. Now B is changing from 0 to VDD. So B is changing from 0 to VDD. This is what? This is a static CMOS inverter. So for static CMOS inverter, if we assume it is a symmetrical device, means symmetrical VTC characteristics, right? Then what would be the logic threshold for this inverter?
VDD by 2.
VDD by 2. So it is around 1.25 volt, right? So now B has started increasing. Okay. So B has started increasing from 0 and it is going towards 1.25. Has not reached it yet, but reaching towards 1.25. So till the entire region, this would be considered as logic 0. Right? It would be considered here as input logic 0. Right? So if this is logic 0, so what would be the output? Output would be equal to 1. So right, then here this would be 1, right? Right? If this is on, now this transistor will open, means on, right? And what about this transistor? What will happen to this transistor? Can you comment? what will happen to this transistor? Okay, okay. Let us focus. Let us discuss with one by one. Okay, so this transistor is on. Okay, so now see, this is on. This is already zero. So it has been shorted with like if it's been shorted with this zero, right? So then till around 1.25, right? 1.25, it would be near about to zero, but yeah, it should be near about to zero, 1.25, right? After that, what will happen? Okay, after that means when it will change from 1.25 volt and goes towards 2.5 volt, this input will, this B will be considered as logic 1. So here it will be considered as logic 1, the output would be at logic 0. So output would be at logic 0. So that means this transistor is now off in the second half, right? Now this is not off, but this is already given as 1, right? And this is a path from here. So what will happen? It will show some type of trend here, right? And follow a trend, something like this. Now please try to explain why it will not reach to the maximum value immediately. Why? Rather it will take a shape similar to like this. Okay, what do you think so? What are the other things that is happening?
So because there is a direct path from A to 0.
There is a direct path from A to 0. Okay. So how does that affect?
I think if we
So
consider A
the
to be drain and F to be source, then VDS is also changing.
If we
So I mean, the VDS of the transistor will also change. So,
VTH of the transistor will also change. Very good point. Why do you
sir,
think so?
sir, VDS, drain to source.
Threshold voltage, right?
No, sir, drain to source voltage.
Oh, drain to source voltage. Okay. Drain to source voltage will also change. So as a result,
So I think it will shift from saturation to linear. That's why such changes.
saturation to linear. Okay. Okay. Do you also think that there is a possibility that the threshold voltage will also change? This is, if this is drain terminal here, this is a source terminal, right? This, as you are as this output voltage is changing, right? Then the source voltage is also changing, right? So try to recall the reverse bias between base and the source. Is it not doing it more reverse bias? You forgot. No, here I cannot write. If this is say this potential is been grounded, say, okay, then is it not changing? Okay, these two are shorted, right? Source and this body terminal are shorted, right? Okay, now as you are changing this voltage, means as this V, this F is changing, Are you not changing this bias? Source bias? Yes. If you are changing source bias, you are changing the bias across the bias of this, right? These somewhere that fixed. So are you not affecting the total threshold voltage, the threshold voltage of this transistor? Yeah. Yeah. Are you aware that the threshold voltage is also dependent on the substrate voltage? No, please do answer. Otherwise, maybe in some time I will discuss that bit more, explicitly.
So basically, body effect was not taught to us in that much detail.
Oh, body effect. Okay. Then fine. So maybe I will take a separate discussion one day, like maybe 15-20 minute discussion on this body effect itself. Okay. Okay, fine. So, like as you mentioned, there are a couple of things that you have to consider, like why this shape should be like this. And anyway, this is not expected like you will be able to get and like manually you will be able to calculate the exact shape. But this is just to demonstrate like if this is the scenario, then what means somewhat this type of nature you can expect, right? To get the exact like type of VTC, you can always do a simulation and which will provide you that, right? Because here many things will be happening simultaneously, right? So that case 3 would be, so okay, the body effect I will then take in a separate class. See if this A and B both are changing from 0 to VDD, right? That would be case 3. And if you do the case 3 as well, na, then also it will be almost similar to this. So here also you can see like the VTC is dependent on the input combinations, right? That is no doubt in that. Other than that, if you notice this is the VTC. If you recall what was the VTC for an static CMOS inverter, like this, V out, V in. This was for the static CMOS case, static CMOS inverter, right? Do you also recall that we have discussed, I think near to the beginning of our class, this course, that there is some property called the regenerative property. If the noise has been introduced, then there should be some characteristics of a voltage transfer characteristic so that it can eliminate that noise, right? And if yes, I think then you can recall that for that the VTC should be like this, somewhere flat, here also flat, in between it should have a high negative slope, right? That is the characteristics of an regenerative circuit. But if you notice this one here, this V output is simply linearly rising with V input, right? So definitely we can make a clear distinction between the VTC of a pass transistor and the static CMOS gate. And from this distinction, you can clearly say from this VTC that this pass transistor logic is not regenerative. Is not regenerative. I hope that you can still remember how have we defined the regenerative property. If not, maybe just go through the our beginning some lectures where we have discussed this regenerative property, I think quite extensively. Okay. So first thing is that pass transistor is not a regenerative circuit, and definitely here you can see the output voltage you cannot reach to the VDD, right? So it is always lower than that, at least one threshold voltage lower than that, right? Okay. So I think these are the basic discussion which is required, and I think we have also discussed regarding the how to connect these circuits. Then let us discuss this part and try to this part also wrap up this part quickly. That is differential pass transistor logic or complementary pass transistor logic. These are type of not very different compared to what we have studied, but it's basically says that you make some combinations, you make some circuits where suppose if you are making AND, then you will get and NAND simultaneously. If you are making something called OR, some get OR, then also design NOR at the same time. Means design like two complementary things simultaneously, and when you design it like that, it is called the differential pass transistor logic or complementary pass transistor logic, because then you have both F as well as the F bar available. Okay, that is the whole motto of this. Okay, differential pass transistor logic or complementary pass transistor logic. So complementary pass transistor logic, also referred as CPL, complementary pass transistor logic. Differential pass transistor logic is referred as DPL. Okay. So now if you notice this one, the first figure here. Okay. Here you have A, here you have B, you have B here, you have B bar here. Here you have A bar, here you have B bar, but the gate, the gate inputs are same, right? This green line indicates that is a connection, and these are the same gate inputs which are driving these two transistors. This same gate here, same gate input here. Similarly for all of them, right? Okay. Now, can you please calculate like what is the function that you are getting here? Anyone for the first this block? What is the logic that you are getting here? Okay, calculate when A0, B0. So when B0, so that means only this transistor is on, right? So B already 0, so that means 0, right? Okay. Now when A1, when like A1, B1, okay, when B1, obviously this is off, then B1, this is on, A1, okay, so both are like 1, 1, so output would be 1. So at 1, 1, output is 1. Okay, let's see the other scenario. Let's say like B0, A1. So B0, A1, so B0 means only this is on. Now B again 0, so that means this is again connected to 0. So that means again 0. Now consider B1, A0. So B1 is this, A0. So that way what you are getting, this is basically AB only. Right. So if this is AB, as if this is AB, then right. If this is AB, then basically what we are getting, like the same function, right? Means see here we have made this AB and we have designed the logic like this, right? Instead of this 0, you could have also make it like B. That also makes this thing, means that will also work, right? Similarly, if you make it here A bar and B bar, okay, and give the same input, you can please check it out. You will get here F bar, and which is equal to A B bar, right? You can see basically it is F and F bar, right? Similarly, here you can give A B, and here you can give B bar, B bar B, and here you will get this A plus B. Here you can just change it to A bar B bar, okay, and here the same input you will get here A bar, which is equal to A plus B bar, right? And here this A bar, this is B bar, this is B, okay, and here this A bar A, this is B bar B, yeah. Here you will get, this is at A, like A XOR B. Here you will get this F bar. Okay, so this is basically the differential pass transistor logic. Okay, both complementary data inputs and outputs are available. So you can see both A bar, B bar are available, and so basically all complementary inputs are available. All complementary outputs are also available. See here, this F bar, like for all of them. Right. But obviously we have seen one some issue. That issue is that this output voltage cannot reach to VDD. It is lower than that, right? So we should do something to solve that issue, right? So here comes the concept of this transmission gate logic, and this transmission gate logic is basically first of all we'll try to address that issue, that voltage 1 VTH voltage drop issue. So for example, if we are designing this like using pass transistor logic using NMOS, right? And suppose if you are charging it from 0 to 1, right? Then you make A1, make C1, right? So that gives a connection and it will start charging, but you cannot really go to go 1, right? Means VDD. You can reach till here VDD minus VTH, right? Charging. Similarly, if you could have made like the same thing using a PMOS, so rather here you give one PMOS na, so we will make C equal to 1 only. C equal to 1 means C bar equal to 0, right? C bar equal to 0. Then see what will happen. This is P, right? So P, it can rise this voltage across from 0 to 1 fully. That means you can go completely to VDD, right? So basically you see this PMOS is good as pull up network. We have already discussed this, right? This good as pull up network, right? This is good as pull up network. However, consider the other scenario where you have to make a change from 0 to 1. So for that you make a 0 here, make it 1, make 0 here, make this transistor on. But then it has to discharge, right? So while discharging, it will not able to be go to completely 0, but it will reach, sorry, it can reach to completely 0 volt. Whereas if you want to do the same thing here, want to go from this, discharge this capacitor from 1 to 0, then it cannot go to the 0 voltage, but minimum voltage would be, right? Minimum voltage would be threshold. We have already discussed it couple of times, right? Then obviously we can say this part is good as a pull up network, right? So then if we can combine the that effect of both PMOS and NMOS, okay, then probably we can solve that charging and discharging issue like this. So here we
Pull
have
down.
this, huh?
It's pull down network. Upper.
Oh, sorry. I have written here pull up network. Yes, you are right. So this is good as pull down network, right? Right. So here, what we will do, we will give it make it like this, right? And we will also do the same thing here. Means just combine these two parallel. Okay. This is C bar. Okay. That makes the transmission gate. Basically, it is transmission gate means what? See, when C is equal to 1, right? A is equal to B, right? When this transistor is on, this transistor is on, it can transmit from one to the other. That's why it is called transmission gate. Okay. And the symbolic representation is like this. Okay. But I always find that this symbolic representation very hard to draw all the time. So I feel that compared to drawing it like this, okay, rather you putting the transistor level symbol and drawing it like this would save more time. Right, see how easy it is to draw transmission gate like this, but rather if you have to draw it like this, then like this, like then here, right, like this. So I would rather prefer to draw this symbol again and again rather than, yeah, but this is just for your information that if you see somewhere this symbol, okay, so that indicates the transmission gate itself, huh? So please note it down, but I will probably not be drawing it here anymore. Okay. Okay, so I hope then this part is clear to you that why this transmission gate would be advantageous compared to the past transistor logic, right? So let me put it this question here so that while you are reading, why transmission gate logic is better compared to past transistor logic, right? Okay, so if this part is clear to you, right, then let us just do one small analysis, which is you can say like like performance analysis, you can say it like this. Okay, let's say performance analysis. Okay, now what do you mean by performance? There are a couple of ways. One is the power, the other one is delay. These are the two important things performance we have seen, right? Okay, now for delay, resistance is an important part, right? Resistance is an important part because delay is basically tau is equal to RC delay only, right? So if we can analyze the resistance, then probably we can also analyze one of its performance, which is in terms of its delay, right? So we're basically going to do that here. Okay, so we have here, draw this thing. This say this is the input, this is the output, this is C, this is C, this is say A, okay, this is say B. Okay, so whenever you say one transistor, right? One transistor definitely, if you just consider in types, some type of large signal definition, then you can always represent this transistor by an equivalent resistance, right? So you're trying to represent get that resistance only. Okay, whether it is NMOS or whether it is a like PMOS, right? You can always represent it by its equivalent resistance. And how do you find the resistance? It is easy. You will do it by simply first find what is the voltage, what is this VDS, right? You find VDS and then divide it by the current that it is flowing, right? So it is basically the large signal. Right. So this is how you can find it. So let us try to see that how these resistances would vary, okay, for a transmission gate if the output is a capacitor and the output voltage has to change from 0 to VDD, right? So output voltage has to change from 0 to VDD. Okay, here one thing, this should be C bar, right? So that we have given here C is equal to like 1, so that, and A is equal to 1 for that to charge. So obviously C bar has to be equal to 0, right? Okay. So in terms of voltage, then it is say 2.5 volt. It is also 2.5 volt and it has to reach to 2.5 volt from 0 to 2.5. Right, this is at 0 volt only. Fine. Okay, so here we are plotting the resistance and here we are plotting this V out, means how the resistance is changing with change in V out, because V out is now charging, right? So it has to charge from 0.5, 0 to 0.5, then 1, then 1.5, then 2, then to 2.5. Say 2.5, 1, Say this is 1 point. Okay, let me, if I'm writing up to this, then why not write the total thing? Right. So V out is this volt. Right. Okay. Then here is the game. The game is we will plot the resistance or the offered resistance for by both NMOS and PMOS. Okay, and what would be the resultant resistance? Resultant resistance, as they are in parallel, it would be the like parallel combination of these two resistances, right? Okay, so then let us break this transmission gate into two steps, means two parts. One is this NMOS, other one is this PMOS, right? NMOS. So this is one. Okay, let us, one means 2.5 volt. Let us write in terms of volt only. 2.5 volt. This V output has to rise from 0 to 2.5 volt. Okay, this is 2.5, right? Okay, so here, what are the, identify the terminals? This is obviously gate. This is obviously drain, higher potential. So this is starting from 0, so we can say that this is the source terminal here. So then how do you find the, okay, then in that case, please tell me in which mode the transistor is operating. This transistor is operating in which mode?
Saturation.
Always in saturation, right? You can see this VD and VG are the same, right? So it will be always in saturation. So it is in saturation. Okay. So can you write then what is R on for this NMOS? That would be equal to this VDS, right? So VDS means basically it is the, so see here, one side it is always VDD, right? It is always VDD. So one side it is always VDD, outside it is V out by this ID sat in, right? Okay. So what is this ID sat in? Can you please tell me quickly, because I want to finish this one in this class. It is VDD minus V out. Okay, what is, please tell me quickly. Okay, there will be some Kn term, right? Kn by 2 into VGS minus VTH. So VGS is basically, so this is V out, right? VGS is basically then VDD minus V out, that square.
Minus VTH here also.
Ah, true. True. This minus, so this is basically VGS minus VTH, that square. Is it correct now?
Yes, sir.
Okay. So, if we say like, this VDD is quite like VD minus V out, okay, is quite higher than this threshold voltage, then probably you can just do a small approximation. I have done this approximation just to check it out. Whatever the plot is given in the book, whether I am also getting the similar plot or not, then probably you will get, see this VDD by the V out, VDD by V out, that will cancel out. Probably you will get a close approximation like 1 by something Kn by 2, and here this VDD minus V out. Like similar to, again, lot of approximations I am doing. This is not a good approximation in fact, right? But to get an idea, right? This would be the R on this R on NMOS, right? So if you actually plot this thing, so what you will see that this resistance, so suppose when this V out is equal to 0, the resistance is like 1 by K in this, right? And if you see, when you are increasing this V out, right, means this it has started charging, right? This voltage is starting build up. Then what is happening to this? This value is actually reducing, right? This value is actually reducing. So earlier you have this 1 by this total V. Okay, let me comment it like this. what will happen to the value of this if this V out rises? Please say it quickly. You have a class now. You have to finish it.
R1 increases.
R1 increases, right? Definitely. Okay. So you have understood it. So R1 increases. So I am taking it granted. Like R1 increases. So and R1 would look something like this, right? Okay. Then can you also do the same thing for PMOS? This is gate. This is 2.5 volt. This is V out, right? So this will be what terminal here? This would be the source terminal. This is the gate terminal. This is the drain terminal for PMOS, right? Right. So you can find the R on PMOS here, and that you can also do by this VDD minus V out. Okay, tell me, this transistor is operating in? This transistor is operating in? PMOS is operating in?
It's also in saturation.
Is also in saturation. Are you sure?
It's
Please
going
explain.
from 0 to 2.5, right?
Okay, it is going from 0 to 2.5. So is this transistor will always be in saturation?
Not always be, but initially.
Initially, true. Initially in saturation. Then say okay. So okay, let me ask you in this question, Shubhaya. What is the in which region for most of the time this transistor will be operating? Is it saturation?
So then linear, I guess.
Yeah, most of the time it is
Diode.
linear, right? You see, you can understand it, right? So only probably up to threshold voltage it will be like when it is changing close to this threshold voltage, only up to that portion it is saturation. After that, linear. So most of the portion it is this IDP linear, right? So you can write that part. So it is VDD minus V out. It is KP, right? Then what? KP, then you have V of SG, right? V of SG is VDD minus uh, V of SG, right? Should I do this? Like, because I'm seeing the time is bit less, so should I do or you can do it? Or let me write it like VSG minus VTHP into this VSD minus VSD squared by 2, right? So if you substitute it, okay, you will get something which would be of I think what I found of this would be in something like this KP, but there might be some, please check it out once. I have
Sir,
done it.
VSG is VDD here, right?
Uh-huh.
VSG is VDD here, right? In PMOS.
VDD
VSG,
minus V out.
it is V out minus V out. Okay,
So
VSG, na?
yeah,
Yes,
that will be VDD.
yes, that, true. That is equal to VDD. Yeah, then it's fine. Yeah, then it's fine. Right. It is VDD minus VTH. Let me write it. And here it is VDD minus V out by 2. Then I think this is square. I think what I got is something like that, but I encourage you to please check it out good once. Okay, so it's something like this, and if you calculate and if you see this from here, if you now increase this V out, if you increase this V out, this R on P will actually fall down, right? Please try to get this nature, okay, whether you are getting this nature or not, that is most important. Okay, so if you do that, you will get some nature which is like this. Okay, so as a result, if you take, so this is R on P, this is R on N, okay, And if you want to take the resultant one would be somewhat probably like this. No, it will be here with this, right? It will be aligned with almost with this here. A resultant. This is basically R on N parallel R on P, right? So please do check it that you are whether you are getting this nature or not. Okay. So this would also help you if you are planning to make and make and pass transistor logic using only NMOS, then you can think about what is happening to its resistance. See, resistance is becoming very high. As soon as this V out is becoming closing towards this VDD minus VTH, right? This resistance is becoming very high, and at V out equal to VDD minus V threshold, this resistance will become almost infinity, because then this transistor will stop working, means stop conducting. That means resistance is almost infinite, right? However, if you see the same thing
Sir?
for this case,
Sir, my next lecture has started.
just a few seconds, okay. And for this one, the resistance will fall like this, okay. So the resultant would be something like this. So here you can see, if you are using an NMOS, if you are using an uh, pass transistor logic, then you see the resistance is like eventually variable. It depends a lot on this output voltage, right? Same thing if you want to do with R on P, means with a PMOS, then also the same thing. However, if it is in transmission gate, then you see with change in output voltage, the change in resistance is almost negligible, right? So that is the message you should take from this discussion. Okay, thank you very much. So we'll meet in the next class. Okay, so thank you for your attention.